Okay, so in today's lecture, we will introduce how to write a program in PyTorch. And before we start to introduce how to write a program in PyTorch, we'll do a little bit introduction about the linear algebra first. So in the linear algebra, um, we have a couple of different objects. The first one is called scalar. A scalar is typical numbers. So just 1, 2, 3 for the typical numbers. And so in the mathematics we have a couple of different operations. The multiplication, the addition, or any functions. So in the scalar we can just write the multiplication, addition, and the function just like in the typical mathematical symbols, mathematical expressions. Then we'll introduce the second data type in the linear algebra. It's called vector. Vector is a list of numbers, contain a list of numbers. So for each vectors, the C is become an array. So we will have a Ci. So I will start from 0 to the n-1 for the n-dimensional array or n-dimensional vector. So those vectors can be add, can be multiply, and can be applied to a function. So their definition is that when we add two vectors, we just add each element together. For example, you add the a plus b equal to c. It means that the ci will become the ai plus bi. And this is the same for the products. So it becomes ai dot bi. And if for the functions, for any function, the sign just an example. For any functions, when we sign of a is a vector, it will become the other vector c. And by definition, the value of the ci will become sign of ai. Okay. So you can see that in the linear algebra, you may remember that there's an operation called dot product. It means that when we multiply a with b, we will transfer a and multiply to b. This is actually exactly the same as the multiplication here. So actually, in the dot product, in the scalar product, we don't really need to write the A transpose here. But if the A is, but actually the A here is exactly the same as the A transpose. You will do a implicitly transpose before you multiply by B. Because in the next object matrix, less is required. But for the vectors, you can either write a dot t multiply b or a just a multiply b. They are the same. The transpose will be done implicitly. And of course, we know that when the dot product between two vectors are 0, it means that those two vectors are orthogonal to each other. Okay, so the next data type is matrix. In the matrix, this is the same. We can extend the addition, multiplication, and function in this way. So there's nothing special here. The only difference is that the a multiply b, this is different. And for the addition and for the function, they are the same. You just write the subscription ij in each to access each element, and apply the function or apply the product to get the addition to the between the elements in the elements wise operation. But for the matrix, it's different. If you still remember in your high school mathematics or in the linear algebra course in the undergraduate course, you have learned that the multiplication from matrix to a vector is like this way. So for each element, we will using a dot product between one row and one column. So for the first entry here is the row 1 and the column 1. And the second row is the row 2 and the column 1. So if both are matrix, so we'll see that the first column if on the first row column 1, second row column 1, third row column 1, and the second column is actually first row column 2, second row column 2, third row column 2. Okay. So from here you can see it's obvious that the dimension of the row and the dimension of column must be matched so that we can do the dot products between two matrices. So from here we can see that this matrix is 3 by 4 and this matrix is 4 by 2. So that since the number of the columns is equal to the number of rows here, so that those two matrices can be multiplied to each other. Okay, so that's a simple introduction to the linear algebra. So that in the next we will try to see how to using the PyTorch to do the linear algebra operations, which is required by the deep learning program. So in PyTorch, we use tensor instead of the NumPy to store the array. So that we need to be able to convert them from NumPy to PyTorch or from PyTorch to a NumPy. So in the tensor, so the tensor is multi-dimensional array. So test is 1D tensor. So because there's only letter by letter in an array. The image is actually a third dimensional tensor because we have a RGB color. So this is the third dimension. So we have H, W, and C. This is 3-dimensional tensor. And if we have a multiple images, which is, for example, which is a video. Video is a 4-dimensional tensor. So N is the number of frames, and HWC is an image. So if you want to access specific data in a tensor, we can access in the following way. For example, in an image, we just consider 2-dimensional tensors. So it's H and W 2-dimension. So if you want to access the pixel 1, 2, so it's the row 1, column 2 here. So we can just using 1 and the command 2. And if we want to access the second row here, so it means, okay, so we just say 1, row 1, and so that's the row 1, and we write just a column without any number. It will access the whole column by this symbol. So this is a new for the Python. So please remember, if there's we can write just a column. It means that the whole column, or we can write the two number before and after the column like this. So the 1, 2. So it means that okay, we will assign the whole column, the whole row, every row in an array, but we only want the column 1 and 2. So it means that this should be less two columns. This column. So this is actually incorrect. Okay. And in addition to the two dimension here, we can add a dimension. You can add an extra number after the two columns here. This means the step. So for example, we're using step 2 and in the row and step 2 in the column. So it means that first we need to select the row 0 and row 2. So they are step 2 here. Okay, the first is column 0 and the second one is not the column 2 because the step is 2 here. So we'll skip the second row and select the third row. And for the column, we do the same thing. So the column 2 here, it will be using to select the column 0 and skip the column 2 and the column 2. Skip column 1 and the column 2. So it's 0, 2, 4. So this operation will actually select only those 6 elements in a tensor. So we can see that the PyTorch provide a very flexible way to access the element in a tensor. So we can write anything here. For example, we can write the A1, 10, 2. It means that we will select the first element, the 1, 3, 5, 7, 9. Those 5 elements out of and the array of 10 elements. So next, we will see how to create a tensor. So we try to start the script so that we can see how it works in real time. Okay, this will take a couple of seconds because in the background the website of the Colab will try to create a tensor for you, create a virtual machine to host the program for you. So it will take a couple of seconds. Okay, so when it's done, we can see the result. So first, we will create a tensor, which has 2 dimensions. The first dimension has 2 elements, and 2 rows, and the second dimension has 3 columns. So all of the element in this tensor will be initialized to be the 0. And the second one is the same, but instead of 0, every element will be filled by an random variable. So this will be very useful if you want to initialize a tensor with the normal distribution. And the third one is the 1. So instead of 0, you need the value to be the 1. And for each of those functions, we can provide an additional the parameters, and those parameters actually additionally. So we can add any number of the variables in any order. After all the positional the parameters before. So the 3 and the 4 are the positional arguments, and those arguments are required. And all the argument after this will be collected as additionally. So for those parameters, you need to give it a name. And so actually all of those non-positional arguments will be collected in an dictionary for the function. Okay, so for here we will load an argument D type, which is to be the type of int torch.int. It means that all the elements in this array will be an integer. So when the PyTorch initialize the memory, you will allocate an integer only instead of a float number. Okay, so for this one, we will ensure that all elements. Okay, so that's how we create a tensor. And we can create the other function to create a tensor is using the arange. So it means that we will create an array whose number is from 0 to 19 by using the arange here. And after we create this array, we can change the shape of it by using the view function here to make, because the return value of arange is an array. It's a 1D tensor. So we can use view to change it to any dimension of the tensor. In here, we change it to the 2-dimensional tensor. So it has 4 rows and 5 columns. So you can see that when we print the A, it's actually an array of 19 elements. But in the 19 elements, and we have 4 rows and 5 columns, just like this one. And we can access the first row of an array. So first array should be this one, is 5, 6, 7, 8, 9. This for first this row 1. And so that the number is row 5, 6, 7, 8, 9 here. And we can access all the rows, but we want to the column 1 and 2 only. So yeah, 1, 3, it means that 1 and 2 not equal the last one. So when you see this, you can see that we want to the column 1 and the column 2 only. Okay, and so we will get every row of those number. So you can see that this is 1 and 2 is here, 1 and 2. 6 and 7 is here, 6 and 7. 11, 12 here is 11, 12 here, and 16, 17 is 16, 17 here. Okay, and then the last one is the most complex one. We get an element by step 2 here. So that when we check this one, we will get the row 0 and step 2. So next one is row 2. So it's this row and this row. Okay, and for the column we do the same thing. We want to column 0, column 2, and column 4. So it's 0, 2, 4 here. Okay, so the first one is 0, 2, 4, and second one we get from the row 2 and get the column 0, 2, 4 is 10, 12, 14. So it's 10, 12, 14 here. So you can try this after the lecture. So you can try in your computer to open and Colab page and do the same thing. Okay, so the next topic we'll introduce is how to reshape in the PyTorch. Okay, so if we have a tensor, okay, this is the other way to create a tensor. We can just paste a multiple dimensional array of Python into the PyTorch, so that you will convert those Python multi-dimensional array into a tensor in the PyTorch. So you can say the torch.tensor and pass in Python array here. Okay, so you can see that when we print the x, we will see the tensor, the PyTorch tensor here, whose the content is exactly the same as the Python multiple dimensional array. And we can use in the view to change the shape of the tensor. For example, we can change it to just one dimensional. So like write 6 here. Okay, so since we have 6 elements, so we can say that. So we can try if we make it 7, what's happen? It will give you an error because the 7 is in value for input of size 6. Because the size of x is in dimension has a 6 element in total, so it's impossible to make it an array of 7 dimensional. So you need to make it 6 here, or if you don't want to write the exact number, you can simply write the -1 here, so that the PyTorch will calculate the correct number for you. For example, we can write in -1, so it will work correctly. Actually, it will be exactly the same as you write 6 here. Okay, so this is very important and useful features. Whenever you don't want to calculate the total number of element, you can just make it -1, so the PyTorch will calculate it for you. This is especially useful when there is multiple dimensions. Sometimes it's difficult or even not possible to decide the number, the size of each dimension in advance. So in this case, we can just write a -1 at any dimension. So whenever you write this one, the PyTorch will calculate the correct number for you. For example, this is -1 and 2. So it means that we want to convert the vector into a two-dimensional array, and then the second dimension has two. The size of a second dimension has two. It means that there is two elements in each element in the second dimension. So, and when you write the -1 here, the PyTorch will try to calculate the correct number here. So it means that since we know that we have 6 elements in the tensor, so the -1 means that this will become 3. So you can check here. We have 3 rows. So even though we don't specify any number here, just specify -1, you will know that because we have the 2 elements in each column. So it means that we must have 3 rows in the entire tensor. And of course, we can put the -1 in any dimension. There will be this two will has the same effect. And the other one is transpose. So when we write the x dot transpose, we'll do a transpose for x. So for here, this will be a transpose. So it's 1 4 2 5 3 6 1 4 2 5 3 6. This is a transpose of the tensor. And actually, we can use reshape to replace the view here. This reshape will be the same as the view. So we can use the reshape is to replace the view here. They will be the same. So an important thing you need to know that when we do all the reshape here or transpose here, the PyTorch won't be real change do the memory copy of the elements. So we can know this by using, we can test this, benchmark this by using the program here. We initialize an array of the 224 by 224 by 3 image, and we have a 1000 image. So this is really a very big array. After we initialize it, we will try to do a reshape here. So this is one dimension. We make it is a 4-dimensional tensors, and by using the view function. Actually, you can see that it doesn't really take too much time for each view function call. So since this is a very big array, this is impossible if we really do anything to copy the element to create a new tensor in here. Okay, the same for the transpose. So actually, for those type of transpose of reshape functions, you just set some property of the tensor instead of do anything. For the view, you just set an array which tells the tensor it has the 4-dimensional and the size of each dimensional. So this is just equal to set an property which is an array of 4 elements. So you should not take too much time. And for the transpose, you just set an array of the order of the dimension. So if we swap 2 and 3 initially the order of the dimension will be 0, 1, 2, 3. So if we do a transport here, the array will become 0, 3, 2, 0, 2, 0, 1, 3, 2. Okay, so actually this won't take too much time either. So you can see that those two elements are they didn't really take too much time. So when you want to do this in the operation, you can just you can just do a reshape transport of it, and then the PyTorch will do the optimization for you. Of course, when you do the transport, when when the PyTorch access the element in the array, you will be using the different orders. So that might be take more time because the element won't not be contiguously. So it means that the first column and the second column, and the number of first column and second column maybe not maybe not adjacent to each other. It will be in a different location in the memory. So the CPU must take more time to access those memory and read the correct element. But in the modern CPU, those kind of index will be very fast. So it should be okay. So the next thing we need to do is to add a new dimension. So in here, if we have a 3-dimensional tensor here, this might be an image. We have a 4x4 image, and each pixel has 3 channel RGB channels. Okay, so in some situation we might to have some put the multiple image together. For example, it's a video, so we need to have a lot of image in order, or we want to calculate the gradient of a neural network in a mini bench. So this we'll discuss this later in detail later. But the only thing you need to know here is that we want to put a couple of different images together. So in this case, we need to have an additional dimension. So initially, our dimension of object is HWC. So we want to add an additional n here. So we can use in the squeeze function to add one more dimension to the A, and we'll return the B. So when we print the shape of B, you can see that we have one more dimension here, and actually we have only one element for now, because now we have only one the image here. And then we can do the transpose between any two dimensions. Okay, and the other thing we often need to do is to permute the data order. So for example, we want to change the shape of data from NHWC to NCHW. The one of them are TensorFlow standard. The other one is PyTorch standard. So when we using the different libraries, you need to know the orders very precisely, so that you can get to do the conversion between the two libraries. For example, if you using one library to read the image from the JPEG file, you need to know exactly how it places the object in the memory is HWC or CWH. And even sometimes the C is the RGB or BGR. They might have different order. So you must be very careful about this so that the data will be correct for when you, especially when you using different library. Okay, so for example, we have the image here, image array here. We have a 1000 image of each of the image is 224 by 224 by 3. So that we want in here it's obvious that is in the NHWC order. So if we want to change it to NCHW, we need to using the permute here. So how can we how should we decide the 4 arguments here? The easiest way is that we assign the number 0, 1, 2, 3 here, and then we put it in a new order because this is 0, 1, 2, 3. So H is 1, W is 2, C is 3. So NC, so N is 0. So we write the 0 here. And next one is C. C is 1, 2, 3. 0, 1, 2, 3 here. C is 3 here. So we put the 3. And the H is 1. And the W is 2. So it's 0, 3, 1, 2 here. Okay, so that's so when you read the code written by others, you need to very carefully to read the permute function. So if you make some mistake, the whole program won't be executed because the dimension of the size of each dimension will not match before when you paste the data into other libraries. For example, when the library want to get one element, one image out of the array, it must know the order of a dimension so that it can access the correct data. So since the NumPy is very popular in the Python, so there are a lot of library which is using to handle the data. For example, load the image and do some multiplication or data augmentation or do some transform. For example, we can apply some filter or we want to resize the image. If you would write those things in PyTorch directly, it's doable, but it might not be always very convenient. So that we often need to convert the data between the PyTorch and the NumPy. Since the NumPy is used by a lot of the existing package or modules right now, so we need to do the conversion between the PyTorch tensor and the NumPy array. So actually that's very simple. And the implementation of a PyTorch has made it very efficient as well. So the PyTorch provides a function called funNumPy, so you can convert the data from NumPy to the PyTorch tensor. And the other way is that we can convert the tensor back to the NumPy, so that, for example, we produce, our model can generate some images, and we want to display those images. So in this case, we need to using some NumPy-based libraries such as Matplotlib to draw a picture, to draw the output picture on the screen. So in this case, we need to convert the data back to the NumPy first. So the next thing is a very important topics. We in many cases we want to move the tensor into the GPU so that we can use in the GPU to do the calculations. So the tensor here, you will include some models. So your CN model or your NLP models, and the data Excel. Okay, so no matter we want to move the data or model to the GPU. Oh, by the way, we need to understand that in order to use in the GPU to do the calculation, the whole model and the whole the samples must be loaded or copied into the GPU memory in advance before we run the program. Okay, so since the GPU has no access to the memory in the CPU's main memory, so that we often need to convert to copy the data between the GPU and the CPU. We need to copy the data from the CPU to the GPU before we run the GPU programs, and after GPU program produce the result we need to copy it from the GPU back to the CPU memory so that the CPU can, for example, draw it on the screen or save it to the disk. Since the GPU cannot access the I/O directly, the CPU is we need to use in the CPU for those jobs. So we often need to copy the data between the GPU and CPU. So if you forgot to do this, the library will give you some warning to tell you that the data is not in the CPU or the data is not the GPU. Okay, so there's multiple way to put the tensor in the GPU. First way is that we just load the data into the GPU directly by using the device argument here. But this is not so useful. Typically, we won't do this, especially if you want to ensure that your program can be run in either CPU or GPU. Typically, we will load the data in the CPU here, and then we are using the to function and specify device equal to something here, so that we can load the data in the CPU. And actually, in the torch, there's a data to test if we have a CPU or we have a GPU or not. Oh, no. Torch. Okay, so this is false. So we can use this function to test if we have a data in a. So later we can, by using this way to decide it. For example, this is the CUDA if and else. Okay, so in this way, you will put the data in the either CPU or GPU. So we can use in changing right in this way. Okay, so by using this way, your program will be able to use in either GPU or CPU. So that if the CUDA is available, it means that we have a GPU, so we select change it into the CUDA here. Otherwise, we're using CPU. Actually, we can write this program to be better to test a couple of different hardware in your system. Currently, we assume that the GPU will be NVIDIA, but actually we will have a AMD GPU, we have an Intel CPU, GPU, or we might run our program in the Mac OS, the Mac OS with the built-in GPU as well, so that we can write a function to test every case and try to make sure if we have any of the hardware in the system, so that we are using it for training. And of course, we can save the data into the disk by using save and load function here. And be careful that when we do this, we must make sure the data is in a CPU. If we are not sure, it always be a good to move the data into a CPU here. And if the data is already in the CPU, we just waste some time to test if it's in the CPU or GPU. So it won't add too much overload to call two functions here. And that will be ensure that when we change the program before, you won't affect the save and load function here. And there is some very important thing we need to know, that when we write the a plus b equal to a, so it means that we will create a new array a plus b and save it into an array a. So this will waste the time to create a new tensor and using a new tensor to override the existing tensors. Because when we override a, we need to free the memory allocated to the old a. But actually, we can do the in place operation by using the program like this. So the effects will be exactly the same as the previous one, but you won't do any memory copy. You will add the value b into the array directly, so you won't create a new array to hold the update version of the a. So there's an example here. We create two tensor a and b and do the a equal to a plus b, or we can just call the function add underscore. They will be the same, but the second one will be more. The performance of the second one will be much better than the previous one, especially for a very large array.